Hey there! You ever just look up at one of those massive, graceful wind turbines and wonder how they work? I mean, they look so simple, right? Just spinning in the wind. But let me tell you, what's going on behind the scenes is anything but simple. Today, we're going to pull back that curtain and dive into the incredible digital revolution that's changing how these giants of clean energy get designed.
So let's just start with the biggest question of all. How in the world do you design a machine that's hundreds of feet tall to not just survive, but actually perform when it's facing down something as powerful as a hurricane? That's not just a hypothetical. That is the real-world challenge for every single wind energy engineer. Yeah, because what we see as a graceful machine is actually a finely tuned instrument that's in a constant battle with invisible forces. It's this incredible high-stakes balancing act, an engineering puzzle that, today, we're going to start piecing together.
All right, so first up, let's really break down what that puzzle looks like. What are the specific hurdles that engineers have to clear to get from a concept on a computer screen to actual clean power flowing into the grid?
Now here's the tricky part. All of these things are pulling in completely different directions, right? You want to maximize your energy output, so you think, let's make the blades bigger. But whoops, bigger blades have to withstand way more stress during a storm, which messes with their structural integrity. And all of that has to work with some really complex aerodynamics. And oh yeah, it has to be cheap enough to actually build. It's this incredibly intricate dance.
So how on earth do you solve a problem that complex? Well, for a long time, the answer involved a lot of guessing and building really expensive physical prototypes. But all that is changing. We're right in the middle of a massive digital design revolution. And this right here just lays it all out. The old way, trial and error, was painfully slow, unbelievably expensive, and just super high risk. I mean, if your multi-million-dollar prototype failed, you were basically back at square one. The new way, digital simulation. It completely flips the script. It's fast, it's cost-effective, and you can test 100 different designs, even break them, in a virtual world without ever spending a dime on actual materials.
And one of the heroes of this whole revolution is a piece of software called QBlade. Honestly, you can think of it like a virtual wind tunnel, a structural stress lab, and an ocean simulator all rolled into one powerful tool. It's basically a digital playground where engineers can build and perfect a wind turbine before a single piece of steel is ever cut.
But how? I mean, how can a piece of software possibly replicate the chaotic, powerful, and totally unpredictable forces of the real world? Well, let's take a look under the hood.
Okay, it all comes down to this incredibly long name, Aero-Servo-Hydroelastic Modeling. I know, it's a total mouthful. But don't worry, once you break it down, it's actually a really smart way of looking at the entire problem. So let's do that right now.
It really just works like this. Aero is all about the wind hitting the blades, the aerodynamics. Servo is the brain of the operation, the control systems that are constantly adjusting the blade pitch and rotation speed. Hydro is for offshore turbines, adding in the immense forces of waves and currents. And finally, Elastic models how the entire structure, the tower, the blades, actually bends and flexes under all of that stress. By simulating all of these things at the same time, QBlade gets a complete, holistic picture of how that turbine is really going to behave out in the wild.
And because they have this complete picture, engineers can start pushing the boundaries into what's really the next frontier of wind power: floating offshore turbines. These things are absolutely key to unlocking the powerful, steady winds you find in deep water, but they have to deal with being tossed around by the ocean 24/7. Simulating that is just critical, and tools like QBlade are what make it possible.
But it's not even just about a single turbine. What happens when you build a whole farm with hundreds of them? Well, you get this problem called wake effects. It's the choppy, turbulent air that comes off the back of one turbine and basically hammers the one behind it, killing its efficiency. So by analyzing this wake, QBlade helps engineers lay out the entire wind farm like a giant chessboard, optimizing the position of every single turbine to get the most energy with the least amount of stress. It's brilliant.
Okay, so this all sounds fantastic in theory, right? But what does it actually look like in the real world? Let's check out the tangible results when you actually put this technology to work.
All right, so here's a perfect little case study. A major wind energy company decided to take their existing, proven turbine designs and see if QBlade could help them make them even better.
So what was the first result? Well, by running just countless virtual tests, they slashed their design and development time by a staggering 30%. We're talking months, maybe even years, just shaved right off the development cycle. That means better tech getting onto the grid faster than ever. But hold on, it gets even better.
The final design that came out of this super fast process wasn't just some minor improvement. It produced 15% more energy. In the energy world, that is a massive, massive leap in efficiency.
So the bottom line is pretty simple. They got a better product and they got it faster. The final turbine wasn't just more powerful, it was also more durable and more reliable, because every single potential weak spot had already been found and fixed in the virtual world.
And this is just so powerful, because it really points to a much bigger story. This isn't just about one company or one piece of software. It's about a fundamental shift in how we are engineering our entire sustainable future.
See, QBlade is a perfect example of this huge trend that's being called digital engineering. It's this core idea of creating, testing, and totally perfecting these incredibly complex systems entirely in the virtual world first.
And the next evolution of this, where things get really wild, is this concept of digital twins. Just imagine a perfect virtual copy of a real operating turbine that's out in the middle of the ocean. This digital twin gets fed real-time data from its physical counterpart, which lets operators monitor its health, predict when it's going to need maintenance, and fine-tune its performance over its entire 20 or 30-year lifespan. It is a total game changer.
And this is why all of this matters so much. Every single percentage point of efficiency we gain, every month of development time we save, every potential failure we avoid, it all adds up. It makes renewable energy cheaper, more reliable, and ultimately more accessible, which directly speeds up our transition to a cleaner, greener planet.
So I guess that brings us to the final thought for today. We're getting to a point where we can digitally design, build, and operate these amazingly complex machines with a precision we've never seen before. And it just makes you wonder, if we can solve a challenge this massive in the virtual world, what other huge challenges in energy, climate, or anything else are we going to tackle next?